Един момент да се наглася. Виждате ли ми вие екран? Виждате ли ми?
Да, виждаме.
Добре ли е или да поправям нещо?
Да е по-добре.
Един момент да се опитам тази долната линия. Виждате ли я с менюто или не да я махна?
Ние не я виждаме. Най-вероятно само ти я виждаш.
Ама аз я
При нас
Виждаме
всичко е
само
наред.
прозореца на Акробат, ако това е Акробат.
Не е Акробат.
Но всеки случай един прозорец виждаме, не виждаме целият ти десктоп.
Да, добре.
Вече си на запис.
Да, добре. Ами тогава да започвам. Значи заглавието го чухте, че ще говоря за семантиката на пропозиционалните атитюди в Type Theory of Algorithms. И започвам на английски. Някой ми каза нещо.
Особено ако почнеш на английски.
Да, точно сега започвам на английски. Сега, just to say that I have included more than I intend to say, just in case somebody is interested, so I can jump between the slides. I'll try to concentrate on 1, 2, and a little bit on 3, what is relevant for the talk, because 3 is the entire system of calculations that I'll present. So I'll start. I have been talking about the syntax and the reduction calculi of the type theory of algorithms many times. So I will try to go quickly through it, although we have new members. So for the new members, I'll quickly say that the distinctive features of this type theory of algorithms, which is under the development, is that it is indeed extension of the classical simply typed lambda calculi, but it's much more of that. So the portions that are shared is the denotational semantics and portions of the syntax of the type theory of algorithms. What is new is this intermediate portion, the algorithmic semantics, and I'll explain how it happens. So the denotational semantics was again to say that it is by structural induction on the terms, which is a standard way of defining the denotational functions. So then I also say something very general, which I already have taught, but recently I have even proved it more strongly with a mathematical theorem, and there is more work on that too. So during the development, how it happens, so Montague intensional logic is the most influential, initial, the first one actually, logical approach to formal semantics of natural language. So he collected most of the logical tools that were available at that time in simple type theory and obtained so-called intensional logic, Montague intensional logic. And he presented a very essential paper, which continues to be influential. And in many ways, we follow those standards for translations from natural language. So from natural language syntax, he presented one-directional translations to his Montague intensional logic. Soon afterwards, Galen presented only mathematical paper, very strong and very essential too, which is already very strong in the theory that I'll present today, by extending Montague intensional logic by adding important portions of the types that were somehow partly done in Montague intensional logic. So then Galen's type system indeed went into more developments of the Montague type of grammars, but I'm not going to talk about that. So then Moskvaki's type theory came as a formal language of the algorithms, of the recursion. So recursion theory, classically, up to now, it is a mathematical structure of functions, with spaces of functions. Muskwakis is putting a connection, Muskwakis theory is putting connection between those semantical domains of functions with a formal language, and I am developing this. So in this theory, in this paper, I am introducing some special operators to solve a very tough problem in computational semantics that has been largely avoided, and especially in recent days, but it was presented in Montague, proposed a solution together with the solution of the ambiguity of the multiple quantifiers. And the solution was profoundly complex and unrealistic. So people have been adapting by adopting portions of it by adaptations. So now I am going to propose to introduce some operators that are repairing those problems from computational point of view. So I introduced two new scopes. So you remember that I introduced the logical operators. So two scope and C, here they are like logical operators. So those who, Mitko Gelev, he's here. So you can compare them with the model operators, but they are not per se model operators because they are more essential for the semantics of the natural language. So they give more direct semantics, semantical representations there. This is not to refute model operators, just to say from start. So here I have been presenting this very often. So I'm switching now to the syntax of the theory. So Muskwakis type theory adopts, here we adopt Galen's type. In situation theory, just to mention, the types are much more elaborated and are already dependent types. But here I stay in this theory, I stay with a simply type system. So 2A and 2C, to 2C, these are traditional already in this type theory abbreviations. So this 2A, 2B, and 2C, they present, they exist in Montague intentional logic, but in Montague intentional logic doesn't exist this the blue S type. S is for context, for state, for I wouldn't say situations because I work on situation theory and I know what are the situations. So this is not a situation, although some people try to say that this is it's not. It is a type in a simply type system. So the other new things that Muskwakis introduced very importantly for the entire system, for the algorithmic calculation, calculations for the algorithmic semantics, are the new kinds of variables. So all variables, all constants, they are typed. But in addition to the typed constants, in each type, there are two different kinds of variables. Recursion variables are what we know for binding operator, binding quantifier, lambda abstraction, and just as free variables in logic languages. Pure variables are completely new. They do not present in any other type system. So they formalize memory cells wherever is the memory in computer, a robot, some other computational technological entity, or the human brain. So here is the syntax. Everything that is in black is classical, comes from classical lambda calculi. 4b is the recursion term, which I have been presenting all the way in all my papers, so I'm not going to talk about it. I proved in a recent paper, not this one, but in another recent paper, that this is not let operator, where is not a let operator, and while the notationally they are equivalent, they are algorithmically different, and let operator originated from Dana Scott. So Dana Scott recently wrote very nice assessment, which essentially is giving me also the question, he's giving me a green light and encouraging to continue with more generalizations. So for C and for D, I developed here recently and presented it for E2. So now the new ones from today are F and G. Before, even if I may not get to the formalities, the entire system, because it is got more for than 1 hour, I'll jump into examples and will present how they work with examples. A cyclicity constraint here is important that it can be switched off. A cyclicity constraint in this type theory guarantees ending, closing off algorithms, calculation steps. But for the belief, for the knowledge, and for many other attitudes, it's important for the self-reference, it's important to have also a cyclic computations. And for that, one needs also more set theory than standard Zermelo-Fraenkel set theory. So I'm not going to talk about this, but I'm telling that just saying that there is a possibility to switch off this constraint, and then we get a more powerful type theory. So now I start with a side example. The possessives, they have been largely also avoided because of their ambiguities. Here, I am not avoiding them. I am using them in my example that will follow. So if you have questions, because I presented this work in a conference recently, and that was important question, so that's why I prepared this slide for them. So if you have questions, I will say, but briefly in the next examples. So actually in the natural language, Mary, this with the capital, is in the natural language. Mary is a possessive determiner, just like the, some, exists, etc. But with more structure in it, syntactical and semantical structure. So one can select, can decide to designate it in this, with this term, relation. So to Mary, but it requires a property. So that's why Mary's sister has to be applied. So relation to Mary has to be applied at first to a property term. And here I choose a simple one, sister. And then relation to Mary's sister actually selects, just like the, it is actually based on the choice axiom. So it selects one, not the unique. It doesn't need to be unique as with the determiners. It selects one of those entities that are in the relation of sister to Mary. That's it. So in the following examples, I will follow this abbreviation, but this is not in the natural language. This is in the type theory with a small italic Mary's S is in the language. So actually apostrophe S is a complex term, relation to. So here is the essential example with which I will present an entire, so this is so to say a pattern, not a pattern, but a specific example representative of a huge class of sentences. So the sentence is, Jim believes that Mary's sister is happy. So here we have two statements, one external and one internal. And the internal one, Mary's sister is happy, is a complement of the syntactically and semantically of the verb, of the binary verb believes. So believes takes two arguments. One argument is, so Q, at first comes the complement. Q is for the additional complement, sentential or propositional complement. or argument, and J is for the subject in the sentence. So one may select, for example, there are plenty of choices in this type theory, and now we'll jump after this one, after explaining, I will jump to my favorite, which I think solves enormous complexity in semantics of natural language. So before I go into the example, I said that this is not a pattern, a representative example. Think about such sentences in the language of mathematics, both in the natural language of the mathematical text, but also in the formal statements. You can believe this directly used in the mathematical text, but you can replace it with states. Jim states that Mary's sister is happy. So I'll show a simple example with states, but here I avoid to use it because actually we have two statements inserted one inside the other compositionally, and if I use the verb states, then I will have three things going on. So that's why I choose believe, the verb believe. Also, Mary's sister is happy can be any mathematical sentence, not necessarily Mary's sister is happy, but n+1 is successor of n, if we are in the world of the natural numbers. So now one can choose to translate directly this sentence into this recursion term. So in here, and here comment, Montegovian translations into this type theories exist. So each one of these components, they are intentional, Carnap intentional by those types S to sigma. So this is abbreviated, but here we have more. Also, in Montague, Q can be the translation of Mary's sister inside, and J can be directly. So I have presented many such examples, and then I try to, I'll skip over them. But here I use an intermediate term, A1. So here I already have removed out of the head term. The entire 2 lines, 9b, is a one single term. And the first one is the head, and then inside of the braces is the second argument of the operator, the recursion operator, where are the assignments, the recursive assignments. So this is a small system of 2 equations. So here I have this special new operator to scope, and its argument, the first argument, is the translation into the theory, into the language, the sentence Mary's sister is happy. So recall that actually in practice, this Mary apostrophe S has to be more complicated term, and then the reductions here will be much more. That's why I prefer to stay with the abbreviation. So happy Mary's sister is actually the first complement. Later, at some point, I'll say why I need this variable for state SC. So now, why I use this scope to scope? So intuitively, informally said, this argument, happy Mary's sister, is the translation of the Mary's sister is happy, but the sentence, Jim believes that Mary's sister is happy, is ambiguous. So thus the description Mary's sister is in the beliefs of Jim, or it is in the way which the speaker, there is a speaker here, there is a user in the situation, in the state SC, who is using this sentence to describe, to tell what Jim believes. So the external user, not Jim, may use the nominal phrase Mary's sister to describe an object. or directly that can be inside of the Jim's belief. That is why it is ambiguous. There are two different interpretations, and now how to represent them. In Montegovian grammars, they just exist two different derivations, syntactical of the sentence. Montague actually disambiguates, creates special artificial syntax of the natural language, disambiguates it to two different tree structures and gets these two different interpretations. So now here the purpose is not to introduce any artificial syntax of the natural language that is not present in the syntax of the sentence, because this is semantical problem, but to represent it semantically. And it is possible to stay with the two different translations, that's okay. But here, a major task of my own, and it seems that it is adopted quite well by researchers already, to go to underspecified term. Generally, underspecification can be handled by meta-language. Here, the value of the type theory of the recursion of the algorithms is that it has facilities with these memory variables, it has facilities to get underspecified semantical representations. And now the question is, which I'm trying to solve, is how to get this underspecified, both these interpretations represented simultaneously, and then how to derive one or the other. So here I presented only one step of derivations, but there are quite many. So actually, to scope is compositional. I add special rules in the calculus, and I get 9D. In 9D, everything in the first argument of to scope, in the blue parentheses, large parentheses, this is already in canonical form, assuming that M apostrophe S is represented by its canonical form. So compositionality of this operator, which I'm introducing, allows me this. So actually, the algorithm for computing the attitudinal complement, the attitudinal proposition, is represented by the first argument of to scope. So here I have chosen this word to scope to designate this operator, to say that the scope is not resolved, because Mary and Mary's sister can be, and even sister, all these subterms, they can be external to this scope, that is outside of the belief of Jim, that can be part of the computations of what the user, the external user, the speaker who speaks about Jim's beliefs is using. So here they matter for the computation of the denotation of Mary's sister is happy, these variables MS, M, and P, but they can be outside of this scope. So this is the underspecification. So now how to get one or the other reading is the next slide. In the next slide, I introduce jumping, to go back. So here, from to scope, suddenly I replace to scope with C. And I keep everything inside as it was in the previous. So I'll show there is a special rule that does that. So actually, with 10A, the scope is resolved in favor of Jim. Jim believes in Jim's beliefs. He believes not, it can be a robot or some system, computational system with artificial intelligence and so forth. So these components, all the components in the assignments here are in his beliefs. So Jim knows how to compute the denotation, this is the interpretation here, informally said. So everything between the blue parentheses is the algorithm for computing Jim's attitudinal belief. And he is aware in his system of beliefs, M designates a particular individual, Mary, and P designates a particular property, sister, and M a relation of some possession or some relation between them. And then he, so this is famous as, then the head of this term is computing the value of this proposition. It might be true or not. So here I'm not concerned with computing the truth. I'm concerned with algorithms for computing truth values, whether they're true, false, or erroneous. So then in the same slide, I present the different interpretation, the Dere interpretation, to go back. So here, to scope, we had all these equations, assignments. Here in the Dere reading, inside of the Jim belief, so C is, I selected it to stand for closure. So here in 10a, the closure closed in its scope all the components of the belief complement. In 11a, all the additional subterm and natural language expressions, there are the user's computations, the user's denotations, the user's assignments. What is in the belief attitude of Jim is only represented by the term, which is the argument of C. So he believes that the individual MS is happy in a state SR second. So, and he doesn't know, he doesn't, or at least the speaker doesn't say anything about the beliefs of Jim, how this object MS is designated. Maybe Jim just sees some object, doesn't know anything about the name or the relation of Mary to, the relation of that individual to Mary, etc. So this is so-called Dere. There are several actually Dere, because some of these assignments, they can go inside of the beliefs. So just briefly to say intuitively, so actually Jim may believe that P is a sister of some individual M, but doesn't refer to M with the Mary M. So here is the significant part. Instead of, which is typically the pattern in natural language semantics, in formal semantics, is each such specific sentence to be translated into a term, and that's it. But again, if I go back here, there is an enormous class of natural language sentences with all sorts of replace the proper noun, the verb, the sentence here, the complement, enormous amount of sentences. Why shall we translate each one separated and do this reductions, etc., etc.? That is what Montague did. And it's formal, it's okay, but not computationally. So now the question is, how do I present all those individual examples with one term? That is possible in this type theory. It is possible directly inside of the language, not as a meta-language. That as a meta-language, people have been talking in one or other way. So if psi is an attitude phrase, in this paper I'm talking only about attitude propositions, but it can be anything else. So, and if I have another expression, phi, that is rendering into a term A of type of the propositions, state-dependent propositions, and if I have psi, this attitudinal expression, translated into a term B, which was here. So here phi is the entire sentence Jim believes, and psi is only Mary's sister is happy. And if I compositionally, if I already have them translated into some terms, then of course I can translate the sentence psi that phi. Oh, here there is a typo. I'll fix that. If you so if you don't see the typo, I will continue without telling about it. Oh, no. It is okay. I'm sorry. Phi is that the complement. Phi is Mary's sister is happy. It's okay. And psi is the translation of some sub-expression, whatever it is. So I have to add something here to make it more clear, even to myself. So now, instead of to show how I get to this pattern and how I can use it, so actually to give me directly 14D is directly instantiation of that pattern. And even I can go furthermore if I select here these translations to be canonical forms. They can be any kind of expression terms, but they can be, that is very valuable, that can be directly canonical forms. And then I don't need to go through entire this sequence of reductions. So here, take a look, I have this term is completely underspecified. I even moved belief inside of the assignment. So this assignment, if I skip it, and if I foresee, it can be later on, it covers entire class of attitudinal verbs or verbal phrases. And similar, of course, for Jim and for the other components. So here is 14D is this more pattern, algorithmically more efficient translation. And again, there are quite many rules here. I only say that these rules are used. This is the rule, which is a new one. I don't know why it doesn't go. Here it is. So actually, this is additional. This is one of the new rules that is significant for these two operators. Here is how to jump from the underspecified scoping, which is pending to be scoped, to one term that is already scoped. C is scopal closure. So what is inside of the closure of this scope is these portions of the initial complement of the operator to scope. Portions of the assignment are taken out, and this means that whatever is translating this closed scope, it is not concerned about the computations of the value of values of B. It's a sequence of assignments and values there, computations, but they can be used. So Q memory variables, they are available to the terms inside of the closed scope, and vice versa. Anything that is computed here is also available inside of the term B. As if we are in the acyclic recursion, then they have to follow the constraints of the acyclicity. So this is actually the most important contribution. Another one is the compositionality. So here, the first ones, application compositionality, recursion compositionality, they are coming from Muscovakis. Here I introduced LQ compositionality in Muscovakis lambda rule is from Muscovakis. I added the pure logic quantifiers exist in A. I presented that to you. And then ST is also a contribution by me. So S such that is an operator that corresponds to the mu operator in recursion theory. So we need it. So I have added it, and it's important one. So now in this paper, we have two rules for compositionality for the open scope, two scope A. If A is reduced to A prime, then of course A prime is inside of the scope of two scope to be scoped, to be scopally closed, pending. So all these reductions that I went through, they use essentially this rule, and the C compositionality guarantees that after closing the scope, it's scope of calculations. After I close the scope of the calculations, then I still can continue reducing the term A to some other reduce A second, A1, etc. So once again, I don't bind directly, don't say that this operator applies, these two operators apply only to attitudinal expressions. They can be used in any terms which target exactly this, to have a term or sub-algorithm A that is scopally open, that can take some of the computations outside and use the values of those external computations. Or here in the second one, in CA, A is already closed, computationally closed. Any computations that are in the argument of C, they stay inside without messing up with external computations. But inside, reductions can continue. So these are the most significant things that I had to say. So I can just go to the conclusion to say thank you. Just a moment, because I don't see the button to do that. So this is, I have much more slides and more examples. I included one with the verb states, because the verb states is essential. So here is general words for what it has been done and what is on the go of working. So in this paper, actually, I extend and add terms that designate statements, including mathematical statements from the language of mathematics. In these days, already there is a significant work for translation of mathematical text, mathematical proofs expressed in natural language, to be translated into formal language, and that this formal language to feed up proof assistants or full automatical provers. And this is ongoing work. And right now, the biggest problem is this, how to translate the natural language into formal language, and that's what I'm working on. So this is what I have to say.
Thank you very much for the speaker. Do you have any questions? If no questions, we have 12 minutes break to the next talk.
I can talk more if you let me.
Not your talk. The next talk is of Dimitrina.
Сега чувате ли ме?
Да,
Да, вече се чуваме, да.
Добре.